Hello, ladies and gentlemen. This is David Rodgers, your moderator for today's live webcast of fiber channel performance, congestion, slow drain, and overutilization. Oh my. We'll give it a couple more minutes to get started here, see what we've got in the way of attendees. All right, everybody. Again, my name is David Rodgers. Today we'll be discussing fiber channel utilization. Our presenters are Ed Mazurek. Ed comes from us from Cisco Corporation. He has over 30 years in the computer networking industry. He spent the first 18 with IBM, supporting VM and VTAM products. Last 14 years, he's been with Cisco TAC Group, supporting IBM networking technologies, and more recently, MDS and storage area networking. He's a tech leader, and he holds 2 CCIEs in integration and storage area networking. He also has 3 lovely performance cars in his garage, totaling 1,364 horsepower. We'll have a quiz at the end to see if you can guess which ones they are. Also with us today is Earl Apellanes. He's a 12-year Brocade veteran, now part of the Broadcom Limited Group. He spent 5 years at Veritas support. He started at Brocade support back in 2005 and has moved into technical marketing. He's now in strategic account sales as an SE, and he's working with Partner Solutions and Sales Group. He's got 2 lovely daughters, one in high school and the other in college, sucking all of his money out of his pocket, so he really needs you guys to pay attention. He loves cars, outdoor fitness, and boxing, so don't get him mad in a street fight. Again, my name is David Rodgers. I have 30 years experience in the computer industry. I spent the last 6 of them directly in test and measurement, focusing on SAN and networking technologies. We have a great panel here for you, and with that, I'd like to pass the baton to Earl. Earl, please take over.
David, thanks very much. Hey everyone, this is Earl from Broadcom. Previously Brocade, now we're a Broadcom limited company. As storage and IT professionals, we all know that the crown jewels of business critical applications, that fiber channel is still the protocol of choice for storage networking, right? Simply because, it's purpose built for high performance, reliability, resiliency, and scalability. Its lossless flow control mechanism is what makes those business critical applications run so smoothly. But when we run into performance issues, what's the best way to determine what's causing them, right? So the primary goal of today's session is to help our customers understand these problems, how to identify them, and how to prevent them from happening. So first we'll cover the basics of fiber channel. It's high level, but detailed enough for understanding how it works. Its lossless flow control uses a buffer credit mechanism, similar to having a token to pass through a toll booth. So understanding how buffer credits work will be key to understanding congestion scenarios that cause these performance problems. Then we'll go over the likely causes of congestion. Understanding these in detail will help to quickly determine the cause of those performance problems. Then lastly, we'll provide some tips on how to ensure that your fiber channel fabric stays healthy so those mission critical applications can continue to run flawlessly. For the rest of the presentation, Ed, Mazurek, and I will tag team the next portions. But the first portion will go to Ed. Let me forward the slide here. There you go.
Okay, thank you, Earl. I appreciate that. Hi, everyone. This is Ed Mazurek from Cisco. Let me talk to you to level set everyone on the basic underlying protocol for Fibre Channel with regard to flow control. So Fibre Channel does have lossless data delivery. Fibre Channel works on a credit mechanism. Frames are only transmitted on the link when it's known that the receiver has specific buffer space to receive that frame. For each frame sent, a R-ready, otherwise known as a buffer-to-buffer credit, and those two terms are completely synonymous, should be returned by the receiver of the frame. And R-readies can only be returned once a frame that has previously occupied that buffer location has been handled. Either it's moved up to other layer protocols, if it's like an end host or something, or it's moved onto an egress interface if it's like a Fibre Channel switch. So once the buffer location where that frame occupied has been freed because the frame has been handled, then an R-ready can be sent back to the sender, and that replenishes his credit mechanism. Now each side informs the other side of the number of buffer locations or credits it has. Now, between an end host or a storage array and a switch on F ports, that happens in the floggy, in the fabric login process. So, for example, a server would send a floggy in and say he has, 8 credits, and the switch might come back and the floggy accept and say he's got 30 credits or 16 or something. The numbers do not have to match, and there really is no negotiation. It's each side just simply informing the other side how many locations that they have. On ePorts for ISLs, interswitch links, it's in the exchange link parameter that flows across the ISL. And it's the same thing. Each side tells the other side what they have. So let's see how this kind of works with a little bit of animation here. So you can see here, this is just pretty much what I've talked about. The end device, the floggy, he tells the Fibre Channel switch how many received credits he has. That is, how many frames the Fibre Channel switch can send to that end device. The Fibre Channel switch, when he gets that floggy, he stores that number of received credits in his transmit credit location. And then he sends the accept to the floggy, and he puts in the number of received credits he has, and the end device stores that in his transmit credit location. So each side's transmit is the other side's receive. And likewise, on an ISL, this happens in the ELP. It's the same exact same. One side's receive, the other side's transmit. And as each frame is sent, the transmitter of that frame will decrement his available credits, his remaining credits for transmit, and if it hits 0, he is no longer allowed to transmit frames until he gets at least 1 credit back. And it really only takes 1 credit because that's basically a binary thing at that point in time where you can either send or not. Okay, so this is kind of the way it works. We have an end device there on the left. It's an end port, and it's talking to a Fibre Channel switch. Could be any kind of switch. And that's an F port, a fabric port. So the end port sends in the floggy, and it says it has 8 credits. And the Fibre Channel switch looks at that floggy and notes the fact that it has 8 credits. And it goes ahead and sends back the floggy accept, saying it has 32 credits. And if you happen to look at the actual switch at that point in time and see what the number of available credits are, you would see that the Fibre Channel switch indicates that it has a transmit credit of 8 and a receive credit of 32, which is just what happened in the floggy. Those numbers should never change. And currently, it has 32 receive buffer-to-buffer credits remaining and 8 transmit buffer-to-buffer credits remaining. So it's keeping track of both how many frames it can transmit and how many frames it's allowing in, and that's the receive credits. So when a port initially comes up and the floggy and the accept the floggy happen, at that point in time, this is what the interface would look like if you looked. Okay, so what happens now? The end device will transmit some frames. So let's see this happen here. And so once one frame gets transmitted, if you happen to look at the fiber channel switch at that exact time, you would see that the transmit credits and the receive credits are still 8 and 32. As I said, those numbers will never change because those were the numbers from the floggy and the accept of the floggy. However, now you will see that there are 31 receive buffer-to-buffer credits remaining because the fiber channel switch, in effect, owes the end device on the left one buffer-to-buffer credit or already. The number of transmit credits remaining is exactly the same because no frames have been transmitted. Okay, so now when the device, when the fiber channel switch sends back a credit, it now replenishes the end device's transmit buffer-to-buffer credits, and you would see that everything is back to full at this point in time. They're both the 32 receive credits remaining and the 8 transmit credits remaining are back to where they were. So this is the basic mechanism of a frame gets sent, the sender of it decrements its transmit buffer credits remaining, the receiver of that frame will decrement its receive buffer credits remaining, and then once the credit is sent back, both of those values would be incremented again. Okay, so what happens if several frames are sent? And this time I'll just use the actual switch to send the frame. So remember, the switch can send 8 frames in this example to the end device. And here what you'll see is if the switch is sending 8 frames to the end device, and once it sends 8 frames and the end device does not respond with any buffer-to-buffer credits, all the buffers are filled up on the end device, and at this point in time, without any additional signaling, the fiber channel switch knows it has to stop sending. It knows that all the buffer positions in the end device are, in effect, full. And if you happen to look at the interface on the fiber channel switch at that point in time, you would see that of the 32 receive credits remaining because the end device hasn't transmitted to it, and you would see that there are 0 transmit credits remaining, and it has to stop. So that's a basic introduction on the flow control on how fiber channel works. And the key thing is that once a device stops sending because it runs out of transmit credits, at that point in time, performance is going to be impacted to either lesser or greater degree depending upon how long it takes for the end device to replenish those credits. Okay, so at this point in time, with that introduction, Earl's going to take this.
Great. Hey, excellent, Ed. Thank you very much for that. So, now that we have a basic understanding and we have a grasp on how fiber channel works, how it helps to deliver mission-critical applications to its users, let's discuss how to ensure those applications continue to perform. So by understanding how to identify a performance issue, you can continue to achieve those, those 5 nines of customer SLAs, right? So let's examine these. All right, so there's typically 3 main causes of congestion in a fiber channel fabric that results in poor application performance. Understanding them will allow you to quickly identify the cause of these behaviors before it severely impacts those applications, right? So congestion can occur when several devices are using the same path through the fabric, just like a freeway when several cars take the same road. the actual point of congestion usually occurs when the common path restricts the flow of frames, and that eventually induces back pressure. And again, this is similar to how an accident or traffic jam can jam up an entire freeway. So first, we'll discuss, what we call credit stalled or slow drain is the most common, reference that you'll hear. But what does that really mean, right? So, as Ed mentioned, it's a lossless flow control, as he presented to us, where a device cannot send a frame without knowing the other can receive it, right? So that's what makes it lossless. But its inherent ability for lossless flow control can sometimes make it susceptible to misbehaving device. And in turn, that usually causes problems for other devices in the fabric. It's kind of like a cascading effect. So in a worst case scenario, a single misbehaving device can have a tremendous effect to performance and other device flows in the fabric. So like in the end, right, Ed showed how a server withholding the return of alreadies or buffer credits, because as he mentioned, those are synonymous with each other, can eventually deplete the switch from having buffer credits to send data frames. So when this starts to happen, it has the potential for that cascading effect to other ports in the fabric, resulting in what we call victimizing other flows, right? So that port can no longer send frames due to its misbehaving nature, and that becomes the point of congestion. And due to that congestion point, it will eventually result in back pressure. So in a nutshell, all other devices communicating over the same link will experience performance problems as well. So a slow drain device, in summary, can victimize other devices and their I/O flows in the fabric. That's the first one. The second, lost credits are typically due to bit errors because of a physical issue on the path, right? The HBAs, the devices themselves, the optics, the cables. These are typically easy to identify because you'll see the port errors on the switch incrementing. Lastly, with oversubscription, this occurs when more frames are entering the fabric than can be drained from the fabric. Essentially, when the speed of frames entering the fabric is greater than the speed of frames exiting. Since the frame, egress rate, exiting rate is slower than the frames coming in, the back pressure can be induced, and this is known to many as congestion spreading. So those are the three, but the one thing I want to note is from a fabric perspective or application perspective, all three may seem similar. It's a performance problem. But specifically, slow drain, the slow drain scenario can appear to be very similar to, for instance, oversubscription. But the difference is how the devices are behaving. In a slow drain scenario, the device is withholding alreadies, right? So the switch can't send frames. And the frames that are in flight in the fabric, those get backed up. That's the slow drain scenario. The oversubscription scenario is when a server is asking for more frames than it can process. So frames are entering quickly into the fabric, but can't exit because the server can't process them fast enough. That in turn also induces congestion, right? So we'll cover these in greater detail through the presentation, but I really wanted to make that clear, and being able to identify these three and having an understanding of what these behaviors are and how to identify them, you can quickly determine which one of these are, right? And, we can prevent them from happening, essentially. All right, so the first cause, right? Simply a slow drain, as I mentioned, is a misbehaving device resulting in abnormal behavior. It's typically a server in most instances that isn't returning already for the switch, right? Or not returning them in a timely manner, causing the requested data by that server to back up through the fabric. So when the switch reaches transmit 0, it simply can't send data. Then it will then have a cascading effect, and that requested data is, backs up all the way to the storage device, right? This is the typical scenario where one device can severely affect other devices in the fabric. So it's important that you're able to understand this behavior so it can be identified and resolved quickly. So both Brocade and Cisco have these tools built in to our platforms to detect this behavior and in many instances resolve it with little to no user intervention. Nevertheless, it's important that you're able to identify these, and so we have these mechanisms in place that can notify the users when this is happening, so you can really resolve the real problem, right? And then so in this following example, it depicts the effects of how a slow-draining device on other devices in the fabric. This is the victimizing scenario I mentioned earlier, okay? All right, let me just advance some of these slides here. Okay, so here, we have a typical fabric topology with a many-to-one scenario, right? That's where a server is talking to multiple storage devices. In this example, the application is issuing a read request to 2 different storage ports. That data is initially received by the server, and its normal behavior after processing should be to return the already. But since it's misbehaving, slow draining, it does not, right? This eventually results in the switch not having buffer credits to transmit the requested data back to the server. As more of the requested data builds up, the frames get backed up. And here's where you'll see the cascading, where you start to see that cascading effect. Then the alreadies are then withheld between the 2 switches. And then the data just continues to get backed up, right? And then lastly, the alreadies are withheld from the arrays. So you'll see, that that any other servers, right? In a large fabric, you have, many servers in this drawing, right? Typically, and many storage ports. It's a many-to-one scenario. You'll see that any other server is going over the same ISLs, talking to the same storage ports or even different storage ports, can get all affected. So if there were other servers in this picture talking to different storage ports, all going over those same ISLs, they would in turn be affected, right? This is an extreme example, but it's been known to happen, right? And as I mentioned before, both Brocade and Cisco, we have these tools in place built into our platforms that can detect these severe conditions. And we can take some action and intervention so it doesn't spread that problem to other devices, to other application flows. So the second one is the lost credit. So this is the second cause, right? The first one was the slow drain. And this one's typically a bit more obvious. When there's a marginal physical link, the switch interface will typically log these errors. The switch would at least be detecting, the transmit counters, invalid transmission words, encoding out errors, depending on the scenario or the switch vendor, right? But ultimately, what this means is frames and credits are not sent reliably, and the entire physical path needs to be examined, right? So typically, if the customer is reporting a performance issue, and one of the links involved is logging bit errors, and you see, on the counters, the ratio of time spent at buffer credit 0 to the number of frames transmitted is significant, we would recommend that you schedule downtime to investigate that physical path of that link, right? And typically replacing the SFPs on both ends, examining the cable, just good hygiene on the physical path, physical infrastructure can help to resolve these scenarios, right? And then for the third cause of congestion, Ed will take us through that oversubscription scenario.
So Earl, Ed, just a second. We have a question from the audience, and I think might be pertinent to our time right now.
Sure.
So with respect to the causation of ISL congestion, if the switch can't transfer the frames due to lack of credits, where would you see the ISL congestion?
Typically in the egress port heading back towards the server requesting the data. Ed,
all right.
You have any comments there?
Yeah, I would say that if you looked at that diagram that we just showed, the rightmost switch, you would start to see a lack of transmit buffer credits on the ISL ports.
Yeah,
and then there would be measured. Yeah, there would be measured. We have some various things. Both Cisco and Brocade have. We actually measure the amount of time a port cannot transmit, and you would start to see that value increment and even skyrocket. So on the fiber channel switch on the right-hand side, you would start to see TX buffer-to-buffer credits being 0, and you start to see what we call TX wait, but it's basically a time that the port is at 0 transmit credits and can't transmit. That would just start to skyrocket, and that would be reflecting of an ISL congestion.
Right. So that egress port. So like as Ed mentioned, the switch on the right, where it has ISLs going to the switch on the left, the egress ports of those ISLs is where you would start to see that, because it doesn't have buffer credits to send frames across to the other switch. That's what you're referring to, right, Ed?
Yes, exactly. Right. So if I look at the question, slow drain really does cause the ISL congestion, and the ISL congestion is reflected by in this example, the rightmost switch, his ISL ports showing a lack of transmit credits. Okay. So I hope that was good. Let's see. Step through. Well, I'll step through to the next one.
Go ahead, Ed. Yep.
Okay.
Yep.
Okay. So let's talk about. So Earl talked about the main, classic quote unquote slow drain. I could say something, the slow drain that we know and love. I don't know. People who've experienced it may not love it, but slow drain is the classic thing people talk about. And it's well known, and it's fairly easy to spot because of things like what we talked about with egress credits going to 0 and that kind of thing. We have both of our companies have good diagnostics on our ports to be able to look at this kind of stuff. Now, oversubscription / overutilization, this is a little trickier, and this is something really, I don't know about Earl, but I've been seeing this just over the past couple of years, 2-3 years, where we've been starting to see these things. And this is something that's really more, it's the absence of slow drain at the edge, at the end devices that's really indicative of this problem. So overutilization is really when more data is available to be sent to an end device than really what the link speed of that end device can really handle. Let's suppose it's an 8 gigabit host. And let's suppose the host issues these SCSI reads, and I know we didn't really go over the SCSI protocol at all here, but in short, a SCSI read command is issued by a host, and then just however many bytes of data come in, or however many bytes of data are specified in that SCSI read, the storage arrays, which are faster and faster, especially since they're all flash and stuff these days, it'll just blast that amount of data in. And so a typical size I see in traces and stuff would be, let's say, 1/4 megabyte. And that would be, I believe, 128 data frames. So one small SCSI read command frame can generate 128 data frames coming back at it. So you could see that if many of these SCSI reads are issued, and they're issued in close proximity to one another, and they're of sufficient size, you could see how more data could be generated by the multiple storage arrays that really could be transmitted on that single link to that individual port. So this could happen, as I see in the third bullet here, this could happen by the storage arrays, because the storage arrays solicit their own data as well via something called a transfer ready, an XFR ready, I have it abbreviated here. But it's not, storage arrays are more purpose-built, and they typically do a pretty good job of controlling the rate of data coming into them, so they don't are not typically the cause of problems. They could be, but they're not typically the cause of problems. But the key thing here in the fourth bullet is that what differentiates this from the classic, as we all know and love, slow drain situation, is that in this situation, our readies are being returned such that the fiber channel switch can always transmit to the end device. The link reaches line rate, whatever it is, which would not be possible if in a slow drain situation. And this is different just since there is no R-ready delay at all in this particular scenario. So as more data is requested by typically these SCSI reads, it will back up in the fabric, and this causes congestion, which looks identical slow drain from the switch back towards the source of the frames, like these storage arrays. But at the edge switch, in the edge ports where the individual hosts or servers are connected, it looks completely different. There is no slow drain indications. There's no credit starvation. There's no already delays. There's none of that stuff. And there's high rate of transmission on the link. So let me go into it a little bit more here. And let me just give you a little bit of little math that I did. So each SCSI read specifies a data length, as I said, in bytes. And typical data lengths are like between 8,000 and 40,000 bytes. Hex 40,000 is, in fact, a quarter of a megabyte. And if you look in the chart here, the time to transfer bytes at various link speeds and size of them are listed there. And let me just use the 40,000 byte example because that's something I typically see. If it's an 800 or an 8 gigabit link, then the maximum, it's going to be longer than this, but the smallest amount of time that to transfer hex 40,000 bytes is over 308 microseconds, the way I have it listed here. And that's just basically taking the amount of bytes and dividing it by the 8 gigabit link rate, and even in taking into account the 8-bit, 10-bit encoding. So let's suppose it's 308 microseconds, okay? If reads are in effect being generated for 40,000 hex bytes more frequently than that amount of time, 800 or 308 microseconds, then it can cause a problem. And let me just show you what what I mean by that. So let's suppose here the reads are coming in, and it's 8 gigabits, and it's 40,000, just like the example I used. And the time to transfer hex 40,000 bytes is 308 microseconds. So let's suppose we have these reads coming in. They're spaced out at 200 microseconds. So every 200 microseconds, we're getting a request, or the arrays and stuff are getting a request to transmit 308 microseconds worth of data. Well, initially that's probably okay, but if it continues, the data eventually is going to build up at the egress port of the end device, the server, and then it's going to build up in the hosts or in the switches, and then across the ISLs and all the way back to the storage arrays. So this is the kind of scenario that I am seeing more of these days. And let me show you this diagram here that's going to look very similar to the one Earl just talked about. So what we have here is we have the server sends these multiple SCSI reads again, and these are closely spaced together. And the storage arrays get those SCSI reads, and they start blasting the data out, because that's what they do, and they're quite good at it. And as the data goes across the fabric from the two switches, you can see the data going across the two ISL ports. The data is going to be sent from the left-hand switch to the end device. Now, this is the difference between what we just talked about, or Earl just talked about. There are buffer credits already being sent back reliably, quickly, such that the fiber channel switch on the left is never unable to send to this end device. In other words, this fiber channel switch is transmitting to this end device at a full 8 gigabit rate. But we have more data coming in than we can really offload to this end device, even at full line rate of 8 gigabits. So what happens? The data builds up on the ingress queue, just like before. This should sound very familiar. And then we start withholding buffer credits the fiber channel switch on the left starts withholding buffer credits from the fiber channel switch on the right. And exactly the same kind of thing, the data starts building up on the ingress queues on the fiber channel switch on the right, on the array ports, and eventually the right-hand switch has to start withholding buffer credits from those two arrays. So at this point in time, the arrays are congested and the ISLs are congested. And any other servers, and there could be hundreds of other servers connected to that left fiber channel switch, any other servers would be impacted because that shared ISLs, those shared ISLs in the middle are congested and are unable to transmit frames, at least for a time. Once the egress buffer is drained, and then they'll start, some credits will flow back. But what ends up happening here is that the buffer-to-buffer credit mechanism that you see here, the R-readies and all that stuff, is basically going to equalize the rate between the supplier of the frames, those two storage arrays, and the receiver of the frames, the FC server on the left. So if the FC server on the left, not a slow drain device, it's accepting things at 8 gigabits, what you're going to see is that those two ISLs are going to be transmitting 8 gigabits of data for the FC server, and those two storage arrays on the right are going to be combined transmitting only 8 gigabit of data. And so this is the difference between the slow drain and the slow drain situation and the overutilization situation. From the FC switch on the left, kind of the right half of that, going back all the way to the servers, it looks exactly like slow drain. So if you were having congestion and performance problems, you would look and say, this is slow drain. But as you made your way, as you followed your troubleshooting, you made your way into the left-hand switch and start looking for ports that are causing this via slow drain. At this point in time, you would say, boy, I don't see any ports that are withholding buffer credits. There is no credit starvation. There is no problem here, so what is the issue? And the issue would be this kind of overutilization thing.
Yeah, so, and a dead giveaway usually would be like that 8 gig link, you'll see it like 90%, 90+% utilized for a long period of time, right, Ed? Is that what you would see? Yeah, you would see, and that's what we used to detect it. We would have some mechanisms to determine high utilization of that link for relatively extended periods of time. And that would be our tell that would help us to identify these devices. But it's not as clear as traditional slow drain. Okay, so Earl, I think you can take it away, and you can show the nice racetrack. Yeah, sure. Yeah, absolutely.
Real quick.
Ed,
go ahead, David. We have a question that may be germane to exactly what we're talking about here, and I think maybe it's a good idea. I'm not certain I can't respond to the folks on the line here and say, hey, we got your question, hang on. But there was a question regarding how would you identify the ports in question? Is there a command in the Brocade director switch? Is reading verbatim on the question here. The director switch is one port. You got it. So yeah, and looking at it from the test and measurement side of things, and I was just thinking out loud. It seems to me that the problem might be that the link is only as fast as the slowest component in this whole chain from end to end. But it's a good question here. I think we should maybe address, and I know you're going to lead into how to do problem resolution, identification and resolution here. So.
Right. Yeah, no. It's a good question. I can address it real quick. So yeah, the question is essentially, if they're seeing these on a port, what commands are there, right? And then Ed can comment on what commands they have. But for us, particularly, you look at port stat show or port error show, and I believe this question came from the slow drain scenario, which would still apply to this, because if you ran like a port error show or port stat show on the switch on the right, and you'll see ports that are at transmit buffer credit 0, right? You'll see that counter incrementing, because at some point in time there was a point in time where that switch could not send frames, right? Or if they're looking at the second scenario, which was The second scenario, let me go back. I'm sorry. The second scenario was the lost credit, right? So in that lost credit scenario, you would see actual physical errors, right? Like, encoding out, invalid transmission words, things like that. And we have counters on the ports, right? Both Brocade and Cisco, we have those kind of error counters, and you see those increments. So if you see those physical error counters, right, it's bit error counters, then that's a physical issue. But if you're seeing transmit credit 0, for a specific amount of time or for long periods of time where that counter is, in the millions, and then you'll see, frames being transmitted at the same time. There's kind of like a ratio of, hey, if there's so many transmit credit zeros and frames being transmitted, then, if there's a certain calculation that we use that would tell us, hey, go investigate the physical path.
And I would just say that for the Cisco switches, we have, for the overutilization scenario, we have something called port monitor, and you would turn on a counter called TX data rate, and you configure it for like an 80% value, and we would get an alert. We record an alert when a port goes to 80% utilization for like a 10-second interval. So it's pretty easy to spot.
Yep.
Once you're looking. Initially, it wasn't so easy, but yeah. So, and the other quick question I see here, do you see discards during overutilization? Let me just say that yes, you can. I could show you an example that I have right here. Not in the presentation, but I could show you an example where we had one server that was running basically at 100% for like 2 hours. And during that 2 hours, we were seeing discards on some of the ISLs in the path to that server. So yes, you could see it, but it certainly depends upon the scope and the scale of the overutilization. All right, take it away, Earl. Thanks.
Yep. Thanks, Ed. Yeah, so I just want to do a quick time check. So here we should be around 40 minutes. We're running a couple minutes short, but we should still be able to get through this. All right, so now that we know the 3 main causes of congestion, how do we make sure that your fabric always kind of looks like this, right? Customers have invested millions in this high performance network, and it should always look and act as such, right? So, along the lines of answering these questions, I understand that everyone's concerned about, how to troubleshoot this, how to prevent it from happening. That's what this portion is, right? So, as I mentioned before, right, so for starters, the vendor provided tools, right? Brocade and Cisco and even the storage array vendors, but for the most importantly, the fabric tools, right? Have those in place. Use them regularly for monitoring, detecting, and alerting. So when these things start to happen, right? In many cases, most customers I find have these tools already. Either they came with a bundle they bought, they're just not aware that they're there, they don't use them. The thing about Fibre Channel is that it works so well, like almost all the time, that you just kind of leave it alone, and they don't think they need to monitor it. But when there is a problem, right, and the problems that we highlighted here are very extreme and they're rare. But when it does happen and you don't have these monitoring tools in place, you're kind of lost, right? So we really advise to work with, your account teams that, sell you these products to say, hey, what are the tools I have, right, and use them, right? That's the main thing, right? There's this old management adage, right? If you can't manage what you can't measure, right? So if you don't have the tools in place, you can't see how the things are performing or not performing when it happens, right? That's the first thing. Second, always ensure that the SAN design is always taking into consideration as the needs of the application grows. And what I mean by that is, as Ed mentioned earlier, in the congestion spreading scenario, right, in the third one with oversubscription, overutilization, that's probably the one I would really look at the most, right? Because you have this 8 gig server, and let's say the application needs have grown, and you just zone more ports to it, right? Not only did you zone more ports to the same server, but you didn't add speed to that server, you didn't change the HBA, you didn't add another HBA, and you just zoned more ports to it. You might have zoned faster storage to it. So now your fan-in ratio of that server has significantly increased, and you're way out of scope of that design for that server. Right? And then that's when you can have those congestion spreading scenarios. Right? You have a large block read, typically a large block read request, and that server ends up asking for more than it could chew. Right? So that's kind of one to consider, is just be cognizant of, you know, the overall design for that application, right? And then, you know, get familiar with these three causes and symptoms of congestion. You know, and that's really, you know, summarizing things, right? So let's quickly recap the three main issues. Slow drain, you know, I feel we've kind of you know, beat that horse to death, right? But you know, as Ed mentioned, the slow drain and oversubscription utilization, those two things primarily look the same from a fabric perspective, right? And so can the loss credit, but the loss credit is, you know, typically easier to find. It's more obvious. But the slow drain and the oversubscription look the same, but the devices are behaving differently, right? As I mentioned in the beginning, and I know Ed mentioned that as well. And the more familiar with these three main causes that you are, the better off you'll be, right, in terms of being able to identify which one it is. So, you know, how do you prevent these from happening, right? You know, prevent, identify, resolve. That being said, you know, here are the things you can do to prevent these things, right? As I said, use these tools, right? We know that identifying these performance issues can be very tricky, and we hope that providing you with the details on how Fibre Channel works, you have an understanding of, you know, the inherent benefits of Fibre Channel, but when there is a problem, how do you differentiate between these types of causes, right? And what tools do you have that will ultimately help you, you know, keep your application running optimally and smoothly 100% of the time. So, you know, that being said, you know, if we have a little bit of time left, you know, Ed can go, you know, since Ed's an expert in, you know, supporting these issues, he sees these customer issues all the time. Ed, if we have a little bit of time, we have a couple of slides left here that'll kind of give the audience here some more meat in how to troubleshoot finding a slow drain.
Okay, sure, Earl, thank you. So, right, so a methodology, so you have to have a methodology. If you're having a problem, you could have a big fabric, multiple switches. Where do you start? So we recommend you start in the following order. You look at how severe the problem is. If you have a problem with extreme delay, like links are even failing and stuff, then you troubleshoot that first. If you're having a problem with like packet loss or retransmissions, like SCSI errors and aborts and stuff in your host logs, then troubleshoot that. But if you see that, but you're having links fail, don't troubleshoot the retransmission or the SCSI errors or drops first, because you're gonna have those if you have links failing. And then likewise, if you just have latency or delay, then and you don't have any retransmissions, SCSI errors in your logs and stuff, and you don't have any links that are failing or anything like that, then just troubleshoot the latency thing. But latency is going to be included in retransmission and extreme delay. And if you just start troubleshooting latency and you got these other twos, then you're going to have latency everywhere and you're not going to know what to do. So definitely look at the most severe indications that you have and kind of troubleshoot the most severe indications first, because that's when you clear up whatever the most severe indications are, that's going to clear up all the things underneath it that are just kind of symptoms of the more severe problem. Okay, so then the other thing is you got to follow the congestion to the source, and this gets back to the understanding the TX credits to zero and the RX credits to zero. And if you just look at, I have lots of people come in to me and say, hey, my buffer credits are zero. Well, the first thing I would ask them is, are we talking about TX credits going to zero, or are we talking about RX credits going to zero? Because if it's TX credits goes to zero, then I go one direction. If it's RX credits going to zero, I go the other direction. So it really matters. You got to be very specific here. Otherwise, you're going to go off in left field. So if you see RX congestion, then you got to find the ports that are communicating with that port that have TX congestion. And if you have TX congestion, then that is a port that's closer to the slow drain problem. Okay, so here we see that we have a port that has 0 RX credits. There's no RX credits, and we then say, okay, let me look in here. We know that port's communicating with the other port, and I look in there and say, oh, TX credits 0 remaining, or RX pause if it's FCOE. And so at that point in time, now I have a port that's got TX credits, delay and starvation. So that would be where you would see it. So at that point in time, we now know that that E port, that ISL port, is closer to the source of the congestion than that specific F port. Now, what do you do when you have an E port? At this point in time, if you have a TX congestion, you have to follow that to the source of it. And if it's an ISL, then you would basically go switch to switch and follow it to the next switch. So if you use these two methodologies here, you'll be able to identify, how severe the problem is, so you know kind of what you're looking for here. And then you would look at, okay, based upon some port, who knows where you're going to start looking. You might start an application, you might start in the middle, who knows where you're going to look. But if you see RX congestion, you got to find the port that's communicating with this and look for TX congestion. And if you have TX congestion, then if it's an end device, then you found your slow draining device. But if it's an ISL, then you have to go to the next switch and kind of iterate through that same process. And eventually, in the case of slow drain, you'll get to an end port that is slow, withholding buffer credits, credit starvation, that kind of thing. Now, if you get to a situation where you don't have any end device that has slow drain, then you're probably in this over-utilization thing, and you can look for ports that are highly utilized and go with that. So, in summary, Fibre Channel is really extremely reliable and robust. If there are problems encountered, then follow the congestion to the source. And there are many tools available in both Cisco and Brocade switches to allow you to identify and mitigate the individual slow drain. There's even commands that you can cause frames that get dropped if you want them to be dropped quicker, just so you can penalize the one slow draining device and kind of relieve the back pressure in your fabric. So almost always the real solution lies in fixing and updating the end device. Typically the switches are not the cause of the problem. So there is another Fibre Channel Fundamentals FCIA webinar that's listed here that you can view for more detailed Fibre Channel information. But that is pretty much it. There's Q&A, and is there any other? I don't think there's any other questions.
So I have a question, and
go ahead
to both of you. And we're talking about how the devices and their logic themselves can create these issues because we're not getting the credits. The device is operating at a less than optimal. The end device is operating at a less than optimal consideration. What effect, and maybe it's another webinar topic for us later on, but what effect do cabling and infrastructure have in these environments as well?
I'm sure Ed will, chime in and probably agree, but it's all about hygiene, right? I mean, that's typically what it is, because I think what I found out, it's been a while since I've been in support, so Ed can probably speak to this better, but we typically assume that the physical is good, right? We take for granted that, everything must be fine physically, just let's look for something, other than that. So yeah, it plays a absolute important role, because without the physical path link being, optimal, it's hard to go past that, right? So.
Yeah, and I'll just say that, if there are physical problems, credits and the starter frame indicator field on frames isn't set reliably, and we can lose credits, and you get into that credit loss situation. So it's very important to have proper cabling and to only run the cables the distances that the individual SFPs can handle. But the other thing I'll just throw out here, because it does matter sometimes, is if you have long-distance fiber channel, then you have to take special considerations there, because long-distance fiber channel requires, especially for ISLs, normally that's where they are, you have to have more buffer-to-buffer credits because you have to handle a round-trip times worth of frames on the link in order to get the credits back, or otherwise the ISL is in a continual state of degradation. So if you do have long distance, then just bear that in mind. There are special considerations that you need to do.
Yep. Yeah, good point, Ed. Yep.
I have a question here from the field. Are there any general rules of thumb about mixing multiple device port speeds in a single fabric? Example, if you got a mix of 2, 4, 8, and 16 gig device ports, what would you expect to see?
I'll jump on that, and I'll say problem.
Yeah. Yeah.
I would say, you know the old saying, less is more. So the less mixing you have of individual speeds like this, the better. I would even go to the point of segregating some of the fabric out using some of the virtualization things like vSANs that we have. But generally speaking, I would not have a 2 gigabit device zoned with a 16 gig array. I would not do that because that is going to cause problems. So yes, less is more, and when it comes to that.
Yeah, and yeah, definitely. And I would just add this is the scenario where, you know, the design thing, right? So if your application was originally designed, you know, was sitting on the server and you had a 2 gig application, and you know, over time, and it's doing the same thing over time, and it hasn't really grown, then it's probably okay. But you know, if your application is doing something different and it's grown a lot, and you're just adding more storage ports, zoning to that 1 2 gig host or 4 gig host or what have you, that's where your fan-in ratios are going to be way off, and then you have that congestion spreading scenario, right? The oversubscription, overutilization scenario that Ed went through, you know, as the last, you know, cause, right? That's really typically what can happen, right? It's congestion spreading is what can happen, right? Because, you know, we've done tests where, you know, the 4 gig talking to a 16 gig, you probably run into that, you know, large block read scenario where, you know, the server is asking for more than it could chew, and then you bump it up to 8 gig, then and it could be fine, right? So, you know, it just depends on what the application is doing and your fan-in ratio. That's what I would add to that.
And we have a comment from the audience saying that their recommendation is to keep the speed mix within 2 speeds, even though an optic will support typically 3. But that person is indicating that's a fairly good rule of thumb, which I would probably agree with.
Like 2 gig to 16 gig is probably not good, right?
No, no, but 8 and 16. And, you know, then you get into, I mean, if you want to drill down into the details, you've got different encoding schemes in these, and then you're asking your logic, your fabric logic, to do a lot of heavy lifting work on that one port. So I think that's, you know, the recommendation being trying to keep it to, you know, 1 or 2 speeds per link would probably be a good idea. We have another
16,
question
32, 8 and 16, yep.
Yeah, 2 and 4, yeah, exactly. We have a question here, and I don't know if we'll be able to answer it in the time, but I'll read verbatim. This person had a case where the interfaces and the tape drives are connected, received transmit credit not available, and credit loss reconnection. The server zoned to the tape drives running at 8 gig are not affected, but the ones running at 4 gig are affected. The transmit only occurred on the interfaces when backup started. Why are 4 gigabits affected and not 8 gigabit links?
And let me take that, because those are, I think, Cisco indications. And I don't fully understand well, they are. I don't fully understand the question, but I'll tell you, TX credit not available means a port is at 0 transmit credits and unable to transmit for 100 millisecond increments. Now, that could be 100 milliseconds, it could be 200 milliseconds, it could be 300 milliseconds, depending upon what it is, how much it increments in a certain interval. And the other one, credit loss recovery, that indicates that a port has actually been at 0 transmit credits for 1 full second. And at that point in time, we initiate credit loss recovery because we think something is really wrong. So in those two scenarios, there is definitely a problem on that end device that is reporting that. It is not giving credits back in hundreds of milliseconds or even 1,000 milliseconds, 1 full second. So that end device could be, it should definitely be suspect. And I don't understand the 4 gig question versus the 8 gig question. I would think servers that are supplying data to both, at both of those speeds would be likely affected, but I'm not positive where the credit not available and the credit loss recovery occurred. But those are very severe indications of credit starvation in a Cisco fabric.
So I suspect whoever is the questioner on this, if they got a hold of their Cisco FAE and or sent you an email with some more detail, there might be some ways to help resolve this, or at least point you in the right direction.
And I'd be glad to do that.
So it's not a question, but I'll read this out loud because I think it makes it's a great way to try and wrap this up. I don't have any more questions on the board here, but from one of our listeners today, we have Ed and Earl. Hands down, the best presentation I've seen on this topic. Your slow drain versus oversubscription clarifications was great. Thank you.
Well, thank you. I have to thank Ed for...
Oh, you're welcome. Yeah. It was great.
Thank you to our audience for participating. It's important that we get this kind of information out from the industry. And when we have upwards of 200 people on a live presentation, pretty good indication that there's a lot of interest in the topic, obviously. And having worked with both of you gentlemen over the past little bit here, I concur. I think it's really good. Oh, we do have another question in here. What about ISL compression and encryption? Any best practices there? Is that a topic for another webinar, gentlemen?
Well, I can just throw out that on typical ISLs, we don't do any compression. And encryption has no effect on the actual performance of the ISL. So you can still, if it's an 8 gig ISL, you can still transmit at 8 gig even though it's encrypted.
All right. This is another comment. Thanks to all. And we have to show the last 2 slides here, which is getting down to the, hold on a second, getting there, Diane. I think it's our contact information. There we go. So this is our next webcast, which is exactly what I was talking about earlier, and it goes to your hygiene and cabling practices. So we have a fiber channel cabling webcast coming up on the 19th of April at same bat time, 10 a.m. Pacific time. This is our registration information. So for those of you that are still on the link and are interested, actually a very, very interesting and important topic with respect to latencies and loss between copper versus optics and things of that nature. And then our last slide here, please rate the event. We appreciate your feedback. The FCIA will post the Q&A blog on our website, as well as we will be posting the presentation later today. Of course, you can follow us on the social platforms with Twitter, and go to our library, download some of the other information that we have. There's quite a few nice tidbits of information. The industry itself, the group of people that are in it, are very passionate about not only what they do, but supporting the architecture and the ecosystem overall. Members like Ed and Earl that are on the T11 and the FCIA, they're valuable resources and they're experts in their field. So don't hesitate to ask them questions and look for other members in the FCIA to help you as well. That's what we're here for. And at that, I think we're pretty much wrapped up, ladies and gentlemen. Anything else you'd like to add? Oh, there's a thank you slide. We have a standing ovation from the audience. So on behalf of the FCIA, I thank Earl and Ed for their time and expertise. And personally, working with you guys is a lot of fun. So thank you very much. And I think with that, we should close up unless anybody else has any other information. Oh, the question, Ed.
Thanks very much, David.
What kind of cars do you have? Because the 1,360 horsepower was a good total hint, but they want to know what do you have in the high performance garage?
It's a 1986 Dodge Omni GLH Turbo, 146 horses. 2009 Cadillac CTS-V with 556, and a 2014 nice. Shelby GT500 convertible with 662.
And that one is the winner for me right there.
Yeah. Nice.
Thanks for asking.
Nice garage. Thanks, Ed.
Yeah, I love it.
All right, bye now.
Thank you,
Thank
David.
you, everyone. We appreciate your joining us. We'll see you on our next webcast. Bye-bye.